Okay, so question number 5. Aluminum chloride reacts with barium hydroxide in an aqueous solution. So that's pretty much the same reaction as our previous question. So we need to write down this equation again. So when we have aluminum chloride, aluminum has a 3+ charge and chlorine has a -1 charge. So therefore we need 3 chlorines to neutralize that aluminum. And this reacts with barium hydroxide. So barium has a 2+ charge, and hydroxide only has a -1 charge. So we need 2 hydroxides to neutralize the barium. And when a double displacement reaction occurs, then we kind of swap our cations and our anions so that they're with the opposite partner. So for aluminum, it'll now be with the hydroxide. And we don't know what state it's going to be in. And we have our second product, which is barium chloride. Again, we don't know the state that they're in. So to find out whether or not these products will be a solid or if it's going to be aqueous, we need to look at the solubility rules. So for example, if you had a compound containing lithium, sodium, potassium, or ammonium, these compounds will always be soluble. So for our case, we have aluminum hydroxide. So if we go down here, we can see that the hydroxide ion is soluble with calcium, strontium, barium, lithium, sodium, potassium, or ammonium, and it's insoluble with any other ion. So in our case, it's with aluminum. So since aluminum's not part of that list, we know that this compound is insoluble, so it will precipitate in the solution. So now let's look at barium chloride. If we look at this chlorine, when you have a compound containing chlorine, bromine, or iodine, this is insoluble with silver, mercury, or lead, and it's soluble with any other ion. So in our case, it is paired with the barium, so this compound is aqueous. Okay, so we know our products now, and to answer the next questions, we just need to first balance the reaction. So we have, notice we have 3 fluorine ions and 2 hydroxide ions on our reactant side, and we have 3 hydroxide ions and 2 chlorine ions on our product side. So to make sure everything is balanced, we just need to put on the opposite subscripts as our coefficients. So for example, we need to put a 2 in front of the aluminum chloride and 3 in front of the barium chloride. And we need to put a 3 in front of the barium hydroxide and a 2 in front of the aluminum hydroxide. So now if we look at all of our compounds, everything should be properly balanced. Okay, so now we can actually start our question. So part A, find the maximum mass of precipitate that will form if 80 milliliters of 0.312 mole per liter aluminum chloride is mixed with 100 mils of 0.315 mole per liter of barium hydroxide. So for this question, it's multi-step, and basically we want to find the maximum mass of precipitate So the maximum mass of our aluminum hydroxide. So to do this, we need to find out which one of our reactants is the limiting reagent. So for step 1 of answering this question, we need to find the number of moles of both reactants. So recall that number of moles can be equal to concentration times volume. So the number of moles of aluminum chloride is equal to, I'm going to convert my 80 milliliters to liters just so that my liters can cancel out when I multiply by the concentration. So 80 milliliters is the same thing as 0.08 liters, and then we multiply by 0.312 moles per liter. So now we get a number of moles of 0.02496 moles of the aluminum chloride. And now for the number of moles of barium hydroxide, we do the same thing. So let's convert our milliliters to liters. So 100 milliliters is the same thing as 0.1 liters. And its concentration is 0.315 moles per liter. Okay, so if we multiply it out, you get 0.0315 moles. Okay, so when finding limiting reagent, it doesn't necessarily end with which one has the least amount of moles, because we have to take into account the mole ratios in our balanced equation. So this brings us to step 2, which is to find the hypothetical number of moles of our product, which is going to be the aluminum hydroxide. So if we had 0.02496 moles of aluminum chloride, and all of it reacts to form our product, aluminum hydroxide, then we know that we needed 2 moles of aluminum chloride to produce, we produced 2 moles of aluminum hydroxide for every 2 moles of aluminum chloride. So I know this because these are the coefficients of my balanced reaction. So basically, they react 1 to 1, and I'll have the exact same number of moles formed of my precipitate. Okay, so we know how many precipitate would be formed if all of our aluminum chloride reacts. So now let's do the same thing for our barium hydroxide. So the number of moles of barium hydroxide is 0.0315 moles. And if we were to multiply it by its molar ratios, we know that 2 moles of aluminum chloride is formed when 3 moles of barium hydroxide reacts and notice that they react at a 2 to 3 ratio. So if we were to multiply this through, you only get 0.021 moles of barium or aluminum hydroxide that is formed. So now we know that barium is our limiting reagent. And the maximum amount of aluminum hydroxide that can be formed for this reaction would only be this 0.021. Since it'll form this much and then our barium hydroxide is going to run out, so we won't be able to form any more product. So now for step 3, I'm going to start a new page. For step 3, we need to now find the mass of aluminum hydroxide that we are the maximum mass of precipitate that will form. So we're going to use the equation mass is equal to number of moles times the molar mass. So we would first need to find the molar mass of aluminum hydroxide. So the molar mass of aluminum hydroxide is equal to the molar mass of aluminum plus 3 times the molar mass of oxygen plus 3 times the molar mass of hydrogen. So if we look up all these values on the periodic table, the molar mass of aluminum is 26.98 grams per mole. The molar mass of oxygen is around 16 grams per mole, and the molar mass of hydrogen is 1.01 grams per mole. So if we add these all up, we get a molar mass of 78.01 grams per mole. So now we can plug that into our equation to solve for mass. So our mass is equal to the number of moles that was formed when barium runs out. So from the previous step, it was 0.021. And then we just multiply by the number of the molar mass, which is 78.01. And you get a final mass of 1.64 grams. So therefore, 1.64 grams is the maximum mass of precipitate, which is aluminum hydroxide. Okay, so that was only part A of question 5. So now we have to try to solve part B. Calculate the concentration of barium ions in the initial solution of barium hydroxide. So if we write out just the reaction of barium hydroxide that dissociates into its ions, you get barium 2 plus 2 OH minus ions. So if we see here that barium and barium 2 plus they're at a 1-to-1 ratio. So therefore, the concentration of barium hydroxide would then be equal to the concentration of our barium ions. So in the initial solution of barium hydroxide, so that means we have 0.315 moles per liter of our barium ions. That's just going to be the same value. Okay, so let me go back to the previous page and we can see what the junior tutor said. For part A, find the maximum mass of precipitate that will form. So they wrote out the reactants and predicted the products, and they balanced, and they found out that aluminum hydroxide is the precipitate. So they calculated the number of moles of both for the reactants, and then they took into account the molar ratios to find the moles of aluminum hydroxide that can be produced. So barium hydroxide produces the less, so it is the limiting reactant. So therefore 0.021 moles of aluminum hydroxide will be produced. So when you convert this to the mass, is on my next page, you get 1.638 grams. Yep. And now calculate the concentration of barium ions. So initially we have 100 mils of 0.315 mole per liter barium hydroxide. And they said that you produce 1 barium ion for every 1 barium hydroxide, so it's just going to be the same concentration. So this solution is correct.